A project has conventional cash flows if initial cash flow is negative or all costs come first, then after that all cash flows are positive. Then there is a relationship between NPV and IRR for such a project. If the NPV is positive for some required rate of return, then the internal rate of return will be greater than this required rate if cash flows are conventional. A project has non-conventional cash flows when we have both inflows and outflows during the life of the investment. What happens then is that we have multiple IRRs. We don't know which one is relevant for our decision-making purpose. Consider projects A and B only. In the case of A, a negative cash flow occurs at the beginning of the period, followed by a cash inflow in period 1. So first we have negative, then we have positive. Compare this to project B, which is mirror image of A. However, a cash inflow is followed by an outflow. First we have a positive, then we have a negative. Once again, the IRR is 30% on both of them. So based on the IRR decision rule, we should accept as both projects have a hurdle rate below the 30% IRR. However, based on the NPV, project B should be rejected as it has a negative NPV. The problem presented here is the lending versus borrowing problem. In the case of our conventional project A, the firm is faced with the decision of either spending the money on the project or investing it at the required rate of return somewhere else. When we invest, a higher interest rate or internal rate of return is desirable. The project is then a substitute for lending and is called an investing type project. In our case, A is a conventional cash flow project and there is no need to modify our decision. On the other hand, for B, the firm is faced with either accepting the project to obtain $100 or borrowing. When we borrow, a lower interest rate is desirable. Project B is a substitute for borrowing and may be termed a financing type project. Here the IRR rule is reversed. We accept the project if the internal rate of return is less than our required rate of return, as it is in our case, and we reject if IRR is greater than R. Because the IRR rule is reversed, financing type projects can be misunderstood. This is the graphical representation of projects A and B. Project A has an NPV of 18. A 10% discount rate with the internal rate of return of 30%. This is an investment type project where we spend money now, we lend out, to receive a larger cash flow in the future, larger repayments in the future due to higher interest rates. Thus, we want a higher IRR and a lower hurdle rate. We see that the higher the discount rate or R is, the lower NPV becomes. So the lower the rate, R, the higher the NPV will be. Project B has a negative NPV of minus 19 at 10%, but the same internal rate of return of 30%. This is a financing type of a project where money is received upfront, like borrowing. However, we want to pay back the money at a lower rate. We want to pay back less. Thus, we want a lower IRR and a higher hurdle rate. We see that the higher the R, the hurdle rate, is, the higher the NPV will be. Only at discount rates greater than IRR we will have a positive NPV. An example of such investment would be a business school, for example, conducting seminars and courses whereby participants pay a fee in advance. The expenses of the investment comes later when the courses start, and the business school have to pay traveling expenses to staff, teachers, salaries, course materials, and so forth. This graph illustrates again the difference between an investment type or financing type of a project. Project 1 is a conventional project like our Project A in the previous slide and should be accepted only when IRR is greater than R, the original decision rule. The lower the discount rate relative to IRR, the higher the NPV. Project 2 is a non-conventional project like Project B and should be accepted only when IRR is less than the hurdle rate, because that is the only time when NPV is positive. The higher the discount rate in this case relative to the IRR, the higher the NPV is. Now consider Project C in the previous table. We can see that the cash flows from C have two changes in their sign. We have a negative first, then a positive, and then a negative again, rather than one we would expect from a conventional investing type project. So net outflow first and then inflows following. If we calculate the internal rate of return for this project, we will find that it has not one but two internal rates of returns. So two discount rates where the NPV equals 0. In general, any project that has more than one change in sign will have multiple IRRs. This confuses the IRR decision rule. The Excel formula for IRR includes a guess, so that the program converges to the nearest most reasonable value. The only way to solve the problem and avoid mistakes is to draw the NPV profile and determine where the hurdle rate falls. The decision rule becomes that we accept the project only if the discount rate or our hurdle rate falls between or is equal to the two internal rates of return. We can see that only then the NPV is 0 or positive. In our case, Project C uses a 10% discount rate, so we are indifferent whether we accept or not, as NPV is 0. The second instance where IRR is unreliable is where we have mutually exclusive projects. This means that if we have two projects, we cannot take both. If we accept one, we must reject the other. An independent project is one that may be accepted or rejected without this acceptance or rejection affecting the decision for another project. In the case of mutually exclusive projects, only one can be accepted, as the projects are alternative proposals. So which one do we have to accept? Logically, we would take the one with the highest NPV and the highest IRR. However, the decision is not so straightforward. Within the mutually exclusive problem, let's have a look at the scale bias first. Imagine I offer you two certain projects. That is, I will always pay. And let's assume that the discount rate is 0%, to make it simple. In the first project, you give me $1 today, and tomorrow I give you $1.50. The IRR of the project is 50%, and the NPV is 50 cents. In the second project, you give me $10, and I give you $11 tomorrow. In this case, the IRR is 10% and the NPV is $1. We said we should accept the investment with the higher NPV, Project 1, and the higher IRR, Project 2. But we must choose only one, we can't have both. Everyone will agree that it's the second project that has a greater value and should be selected, even though the internal rate of return of the first project is greater. The inconsistency arises because the IRR ignores the questions of scale. It will always bias towards smaller projects than larger ones, even if they offer the same NPV. Looking at our example with the Australian project, and the European project, we see that the Australian project has the higher IRR but does not increase shareholders' wealth as much as the European project. Faced with the choice of increasing shareholder value, and assuming we have enough capital to invest in the larger project, we should choose the European project based on the NPV only. So always use that net present value to make your decision when there are any problems with the IRR. The other mutually exclusive problem has to do with the timing of the cash flows. Consider the two mutually exclusive projects, A and B, where we have calculated the IRR and NPV at 9%. Project A has a higher cash flow early in its life, while B has a larger cash flow later in life, in year 3. The IRR criteria favors A, but NPV favors B. Again, we can only choose one project only since they are mutually exclusive. From the NPV profiles in the graph, we can see that the NPV of B is higher at low discount rates, but the NPV of A is higher at high discount rates. The NPV profiles of the two projects cross over at a certain rate, at 10.55%. At this rate, both projects have the same NPV. We call this rate crossover rate. Now we modify the decision and it becomes as follows. If the discount rate is below this crossover point of 10.55, we should select project B, the blue line on the left-hand side of the crossover rate. And if the discount rate falls above the 10.55, the crossover rate, we should select project A on the right-hand side of the crossover point, the red line. The problem with the IRR is that it favors investments with short-term payoffs over those that offer a long-term payoffs. When we have mutually exclusive projects with different timings of cash flows, always choose NPV to make the decision. Which project adds value the most? Remember, that should be the important question that needs to be answered. In our case, project B, because it has the highest NPV. With the NPV, cash flows are assumed to be reinvested at a discount rate, which is the cost of capital, while the internal rate of return assumes the cash flows are invested at the IRR of the project. NPV assumption is more realistic as projects' cash flows reinvested at the required rate of return or the cost of capital. It's more realistic assumption. In the case of A, the large inflow, which does not provide any benefits at low discount rates, will start to be reinvested for the remaining term of the project as rates rise. B, on the other hand, will be penalized because its large cash flows are very late in the project and therefore will be heavily discounted. Therefore, for project B, it's better to have a lower discount rate. And that's why at 9% we choose B as it has the highest NPV. Note that the NPV profile of B is steeper than the NPV profile of A, meaning that NPV of B is more sensitive to the discount rate than A. The NPV criteria will always select the most appropriate project regardless of the discount rate.